Welcome to lesson 4 for trigonometric modelling. This is chapter 7, year 2 pure maths. And today we're going to look at using the addition formulae. So the addition formulae that are given to you in the formula booklet, stipulated here. And we're going to use them to simplify expressions like this. Now, these are commonly known as harmonic trig functions. Okay, or trig expressions, and we'll learn more about that later. Obviously, you're going to need some solid knowledge of year 1 trigonometry all the way up to the identities and equations. And if your algebra is good, that's also a plus. So let's get started. Could you please pause the video and have a go at the 4 warm-up questions, please? Okay, and let's have a look at the solutions. So for our question 1, it's another classic case of spot the identity, isn't it? And if you notice, we've got a coefficient of 2 in front of both the cos squared and the sine squared. So it'd be a good idea to factorize that out if you haven't spotted it already, and then hopefully it will reveal itself to you what I'm talking about. So this would be exactly the same as taking the 2 out of the front, and then you would have obviously cos squared x plus sine squared x, like that. And you'll know from experience from last year, cos squared plus sine squared is just identical to 1. It's not equal to 1, it's identical. Doesn't matter what x is, as long as it's a real number. So this is just going to be identical to 2. So it's quite a simple start, but maybe this is going to be useful later on. Moving on to question 2, we're given 2 relationships, sine and cos of some angle alpha. And we're told alpha is an acute angle. Now, how do I know that? Well, it tells us here. It's between 0 and pi over 2, not including pi over 2, of course, because that would be a right angle. And we have to find tan alpha and the actual angle itself. So for part A, we've got 2 ingredients here, haven't we? We've got this cosine part here, and we've also got the sine part. So think to yourself, how do we form tan using those pieces of information? Well, there's another identity, isn't there? I'm just going to make a note of it before we start. We know that in this situation, or any situation, we would have the tan of alpha would be identical to sine alpha divided by cos alpha. All right. Okay, so let's see what we can do with this. Well, sine alpha, I can get that just by rearranging this equation here. So I'll do that. We've got a bit of space at the bottom. So for part A, I can say that, well, sine alpha is just going to be 12 over 37. And I can also use the second equation here. Cos alpha, just rearrange it, make cos alpha the subject, is going to equal 35 over 37. And interesting, we've got 37 here. Now, I think what would the relationship be between these 3 numbers, the 12, the 35, and the 37? Well, I'll let you explore this, but you'll probably realize this is going to be a Pythagorean triple because we're talking about the adjacent, the opposite, and the hypotenuse of a right angle triangle with an angle alpha inside it. So let's move on. So the tan alpha is simply going to be the sine alpha divided by the cos alpha. So I'll write them explicitly. So the sine alpha is, of course, 12 over 37. And then I'm going to divide that by the cos alpha, which is 35 over 37. All right, and it looks complicated, but remember, we can clear this fraction really easily. We've got the same denominator in both cases. So if I multiply top and bottom of this fraction by 37, you can see that this will just clear. So the 37s will clear here and there. And you can very, very quickly, you don't have to do all this working, of course, you can very quickly get to the answer 12 over 35. All right. And that just tells you a bit about the triangle I alluded to a moment ago. So if I just wanted to draw this triangle like so. All right. And we know the angle alpha would be maybe here. Okay. It doesn't matter as long as I label it correctly. We have an opposite side. Well, remember the tan is opposite over adjacent, isn't it? So we could say proportionally, the opposite side would be 12, the adjacent side would be 35, and we also know a bit about cosine and sine. So just use the cosine. This must be the hypotenuse. Okay. So we know a lot about that right angle triangle. In fact, everything about it, if necessary. So there we go. So I think that concludes it. Now we have to look at the angle alpha itself. So we'll do that. So for part B, how do we get the angle alpha? Well, it's quite straightforward. You've got three choices of how to do this. So I could simply just take, let's use the tan part. So it would just be the inverse tan of the 12 over 35. Like so, or you could have done the inverse cos or the inverse sine. It doesn't really matter. So I've got my calculator here. Now my calculator at the moment, you've got to be careful with this, is set to degrees. Okay, you see that there? So the D option. So what I need to do is make sure that I'm actually set to radians, because in the question, the angle alpha is defined in terms of radians. Okay, you can tell by the fact that this angle here is pi over 2. Okay, let's just show you that again. So there we go. All right. So just to set it to radians, okay, so what we need to do is go to Shift and Setup, all right, and change the angle unit, which is option 2, to radians, which is also option 2. And you'll notice now we've now changed to the R, which is radians. And now we're good. So we can now just say, okay, Shift and tan, and put 12 over 35 in, however you want to do it. Just come out of that fraction if I can. Press equals, and there we have it. So does it specify a accuracy? No. So good exam practice would be, let's do this to 3 significant figures, as is the standard rounding. So this is going to be 0.330 to 3 significant figures. All right, so that's question 2 completed. Okay, now for question 3, we have to describe transformations of y equals sine x. So this would be the parent function. And we want to get the graph y equals 2 sine of x plus pi over 3. And then we have to state the maximum value. Well, when we're discussing transformations, the first thing to note is it's the transformations in the x direction, or the horizontal direction first, which is contained inside those brackets, or inside the pair of brackets. So we've got x plus pi over 3. Now we have that rule, don't we, inside opposite. So just as a shorthand, before we write this properly, I can tell that because I'm adding here, although it's counterintuitive, it means I'm going to be doing a shift in that direction by pi over 3, okay, to the sine graph, to the graph y equals sine x. So that's the first thing to notice. And then for the second transformation, we notice we've got this 2 at the front of the function, which is multiplying the sine function by 2. Now, because this is outside the function, this is a transformation in the y direction. So that 2 tells me I must be doubling my y coordinates. Okay, so how do we write this formally? Well, for part A, we can do this properly just by calling on a bit of prior knowledge and just using a bit of common sense. So for part A, will let me write. No, it's not letting me write for some reason. So for part A, we could say y equals sine x is, now because it's a shift, isn't it? It's a shift by pi over 3 to the left. The proper name for this is, of course, a translation. So we say it is translated. So if the graph or the object, whatever it is, maintains its orientation and it is not distorted in any way, it is simply placed somewhere else on the 2D plane, that's called a translation, and it's a past tense, so it's translated. So y equals sine x is translated, and we can describe translations using the vectors. Okay, so we just need a vector that would just shift my shape pi over 3 to the left. Okay, so let's do that. So it would be, well, first of all, it's not changing in the y direction, so that would be 0 there, and we would need to put a negative in there just to show that it's going to the left. Okay, so that's the first transformation. So just to recap, and anything you may have forgotten about this, it's a translation, and for translations we can describe them using vectors, and the number at the top of the vector is the change in the x direction. So it's describing the vector that takes it from the point where you're at the moment to another point in the x direction, and then it's the same thing at the bottom, but in the y direction. So it behaves kind of like a coordinate, a pair of coordinates, I should say. So that's the first thing. Now the second thing is the stretch in the y direction. So we could then say y equals sine of, now we've completed this transformation, of x plus pi over 3 is stretched okay, and the scale factor we know is 2. So you always need your scale factor. A scale factor of 2, and specify the direction in the y direction. And we know that because the 2 is out on the outside of the function. So those are the two transformations. Okay, I hope that makes sense. So you just to reiterate again, I just want to summarize what I'm saying. You've got the stretch there, okay, and then you've got the scale factor, which you also need, and you need to specify the direction in which coordinates are affected. All right, so that's that. Now for part B, we have to state the maximum. Now there's no build up to this, it's just a case of stating it. Well, we can talk about it a little bit. We know a little bit about the sine graph, don't we? If I just do a rather crude drawing of the sine wave, it behaves kind of like this. Now, irrespective of whether it's translated or not in the horizontal direction, the range won't change, will it? Because if it's shifting from left to right in the x direction, nothing happens to the range. But because I'm multiplying my function by 2, okay, this is going to create a stretch, okay, in the y direction, and that will affect the range. Okay, so if we've gone from a maximum value of 1, which is how sine is defined, and a minimum value of -1, then obviously if I'm stretching by a scale factor of 2, this maximum now is not going to be at 1, is it? It's going to be at 2. So that maximum is going to be at 2. And similarly, the minimum is going to be at -2. Okay, so it's just a bit of a crude sketch that. So we know, if you just want to summarize it a bit differently, we know that sine x is bounded between -1 and 1. Okay, again, it doesn't matter about the translation horizontally. This is also still bounded between -1 and 1, and then the only change comes when we double on the outside. So it's going to now be bounded between -2 and 2, just by multiplying everything by 2. Like that. All right. So there's just different ways, different paths you can take just to get to the same conclusion, which the maximum value is, of course, going to be 2. I hope that's okay. Now then, for question 4, it's the same process. Okay, so I'll just put those on the board and hopefully just have a quick look at it, make sure you agree, and then we can move on to the main content of the lesson. All right, so I've just put the answers up for question 4, so you didn't have to watch me just writing them out. So let's just talk about them briefly. Again, we've got a translation for the first part because we've got this -π/4 inside the function. And we have that inside opposite rule, don't we? So as a shorthand, before you write any of this out, you may want to just say, okay, well, because it's negative, that means it's going to be moved to the right by π/4. Okay, and I've described the exact same thing using the vector π/4, 0. So as you can see here, it's moving the graph by π/4 in the x direction, 0 in the y direction. So that's the horizontal shift. And I've stated also again that it's a translation. Once we've done that, we can then perform a stretch in the y direction because we now have this √3 as a coefficient in front of the cosine. And you'll know from the previous example and probably from earlier, this stretches the graph by a scale factor of whatever that constant is. So it's scale factor of √3. Okay. Now, I've just stated the max value because I didn't read the question properly. It asked for the minimum value, which I should have read. Now, if you remember from the previous question, I'll just state it. The cosine function is bounded between -1 and 1. And so is the cosine of x subtract π/4 because that is a horizontal transformation. It has no effect on the range. So I'm basically just writing down the range there. This means that if I want to multiply everything by √3, I'm going to get the following. So this is going to become -√3 cos of x subtract π/4. And then the upper bound is, of course, going to be √3. So I can now state what the minimum value is. I've stated the maximum, so we're going to get 2 for the price of 1 here, aren't we? This is the good thing about it. The maximum value is on the right-hand side, but this is the minimum value. So you can't get a value any lower than -√3. So I'll just write that down just to finish this off. So the minimum value will be -√3. So I hope that's clear. Right, so before we get into some worked examples, I just want to go through the intuition behind what we're going to be looking at in today's lesson. And I've presented you with a diagram, which is a graph of some sort of trigonometric function, which we're just going to call y = f of x. So I've just stated that here. We don't know anything else about it other than we'll just generalize in that way. So some function of x. You can see that the x-axis is defined in radians. I'll just make a note of that. That's something important to bear in mind. And the y-axis will return whatever value of this trig function you'll get when you plug in any of these particular angles in radians, of course. Now, the task I'd like you to do first, before I talk through the idea behind today, is I'd like you to look at the diagram carefully and try and figure out what the equation of this graph would be. What actually is the function that we're looking at? And there's lots and lots of clues on display here that should enable you to write down what this function actually is. So what I'd like you to do is I'd like you to write it in two ways. The first way is as some kind of transformation of the sine function. So I should probably just scroll down, or maybe not. We can see it, can't we? So some sort of transformation of the sine function. That would be one approach. But you could also write it as some kind of transformation of cosine. Okay, as we can see here. So I'd like you to write it in two ways. So please just pause the video, think carefully, and then we'll go through the results. And I'll try and prove to you that they are indeed correct. All right, so you've had a think. And if you recall questions 3 and 4 from the warm-up, there's some massive clues there, isn't there, into the line of thinking. And let's consider case 1 first. And I know this is sort of written at the bottom of the page, but I just like to sort of write next to the graph so it's clear what I'm talking about. So the first thing to notice from this trig function is the maximum value and the minimum value. I think that stands out the most, doesn't it? So you'll notice the maximum value occurs at 2, and we have a minimum value here at -2. And we know a bit about the sine wave, don't we? If I just do a little sketch over here of the sine wave like this, so I'll just draw it rather crudely, but there we go. So we know a bit about the sine wave. So we'll call this y equals sine x, our parent function. And under normal circumstances, if this was just y equals sine x, we would have a maximum value at 1 and a minimum value at -1. That's the range of sine x, and it doesn't go beyond that. And if you notice from what we've got here, we have a range that begins at -2 and finishes at 2. So that suggests we've got some kind of y transformation going on. And it looks like we've got a stretch scale factor 2. So that's an important step. So I could probably write as my initial sort of hypothesis here that the graph we've got in front of us is some form of y equals 2 sine x. I know that's not the correct answer, but I put the coefficient of 2 in, which would give us the correct range. So I've accounted for the range, and I'm pretty confident that's going to work. Now, the question is, of course, it's not sine, though, is it? Because we know sine, whether it's multiplied by 2 or not, sine passes through the origin. And you can see this on my sketch. Although it's not the best sketch, it passes through the origin. And this clearly does not pass through the origin. It passes through the point -pi/3. Okay, and then we have another x-intercept at 2pi/3. A normal sine graph doesn't do that. Of course, it has the x-intercept at 0, and then on the other side of the symmetry, we have an x-intercept at pi. So there must be some kind of translation going on as well. Well, if we assume this sine graph, which would have passed through the origin, has been shifted to this point here, okay, that shift is by pi/3 radians, isn't it? It's moved pi/3 radians to the left. Same over here. So that's 2 squares on my scale. So it's moved by pi/3 radians to the left. It's gone from pi to 2 pi over 3. So clearly I've subtracted pi over 3. Now, that's a huge clue, isn't it? So that tells us it's the sine wave, but it's been translated by pi over 3 to the left. So in other words, the vector, it's been translated by, I can write it down as negative pi over 3 and 0 in the y direction. So how do we write that in the function? Well, it's inside opposite, isn't it? Okay, so inside opposite would suggest that I must add pi over 3 inside the function. So I'm going to have y equals 2 sine of x plus pi over 3. So I think that would be a suitable candidate for my sine transformation. So I'm going to make that look really important, and we can write this in the space provided shortly. Okay, I'm sure you've done that already. So I'm just going to make that look important. I think that's my final answer. Okay, and now while we're doing that, we've got to consider how would this contrast if it was a cosine parent function. Well, there's numerous ways of doing this, okay, and a lot of the work has been done for us already. Okay, we know because of the scale factor stretch of scale factor 2 that this graph has been stretched from -1 to -2 and from 1 to 2. So we know that stretch is there. That's been done already. So I know my function, if cosine is going to be my parent function, it's got to be something along these lines. Okay, I know that's not correct, but at least I know my range is correct. So now I've got to look for some kind of translation from the cosine function. So let's sketch the cosine function just to familiarize ourselves with what's going on. So I'm just going to sketch this. Now the cosine function is not quite the same as the sine function, as you know, but they are translations of each other. So if that's my x-axis, my y-axis there, just a sketch, of course. Now this time, let's have a look at the x-intercepts. Well, no longer do I have the origin as an x-intercept. Okay, so the x-intercept is now at pi over 2 and at 3 pi over 2. Okay, and we have maxima at 0 and 2 pi and a minimum value at pi. All right, so that's where the cosine graph would be sat, if you like, on the 2D grid. So how can we translate my green sketch to get the graph that we have presented in front of us? Well, just to make things a little bit clearer, I'm just going to rub out what we talked about earlier for the sine function, just so we've got something a tabula rasa, if you like, something we can start afresh from. It might be a good idea just to consider the maximum values, because if you notice on this sketch, the maximum has now shifted to here. Okay, so it looks like it's moved. I say moved, I'm moved in inverted commas. It's moved that way by 1 square. Okay, that's plausible. So it looks like we've got some translation of pi over 6. So it's only 1 square, so it's pi over 6. Okay, can we confirm that? Well, yes, we can. If you look at where the x-intercept would lie for the cosine graph, that would be pi over 2. It's now shifted pi over 6 to the right. Again, okay, everything is consistent. So we know that this is now translated by the vector pi over 6, 0. Just trying to squeeze that in. Let me just rewrite that bracket. So that's pi over 6, 0. So pi over 6 along the x direction in the positive direction and 0 in the y direction. So how does that materialize in the function itself? Well, it's quite easy. It's inside opposite, so I have to put a minus sign in front of that pi over 6. So it's going to look like this. So it's going to be 2 cosine of x subtract pi over 6. All right. And that looks like a suitable candidate for a cosine parent function. So that's so you can see how they can contrast. So the ranges are the same, but obviously the translations are different because sine and cosine are obviously translations of each other. So let's check now whether these ideas are actually correct or not. Okay, so what I've done now is in the space that you've probably provided, oh, sorry, not you provided, but in the space I provided for you to write down these functions, you should have 2 attempts at that. Now, what I'm going to do is I'm going to try and convince you, hopefully, that these functions are indeed identical. Okay, and we can do that using GeoGebra. All right, so here we have a GeoGebra window open. What I've got here is I've got an x-axis given in terms of pi, so I can probably zoom in a little bit actually. And if you notice on the left-hand side, we've got 3 graphs ready to be plotted. So the first one, the green curve, this was the first sketch that we deduced, if you like, or the first sine function that we deduced from the sketch, I should say, using those 2 translations. And you can see clearly you've got the maximum value at 2 there and at -2, and it's translated by pi over 3 to the left, of course. So that's the sine function. Did I say the left? I think I meant, yeah, sorry, beg your pardon, to the left. Yeah, that's right. Now, also we've got the cosine version of this, and if I just overlay that, you can see that they fit perfectly. So these are indeed the same curve. All right, they're just translations of each other. Remember that sine is a 90-degree or a pi over 2 translation of cosine anyway, so it makes sense that these would naturally overlay if you use the right kind of translation inside the function. And also you need to have the same scale factor on the outside to make sure that the maximum and minimum values are coincide as well, and also the other values, because there will be a distortion otherwise. Now, I've also got this one here, this function h. Now, you'll notice this is sine x plus √3 cosine x, and this is of the form a sine x plus b cos x, which is that harmonic form I mentioned at the start of the lesson. Now, if I overlay that, you can see again, h coincides with both f and g. So although it looks as though this curve is either just some transformation of a sine curve or some transformation of a cosine curve, it can also be represented as the sum of sines and cosines as well, which is quite surprising. And that's what we're going to get into now. So I'm going to show you how to take this particular or the forms we've just looked at and deduce or derive this particular harmonic form. So we're going to do that next. All right, so back to the notes. I've just written up those 2 functions again. And if we look at case 1 first, we're going to apply our compound angle formula for this. So case 1, we can use the sine of a plus b identity. It's called a formula, it's also an identity, isn't it? Right here. Again, this is provided for you in the formula booklet, but I thought just for the sake of ease, it's nice to have it in front of us, isn't it? So we can reference what we're doing. So the question is, how do we use this? Well, if we look at the function that we wrote down, we can see candidates for a and b, can't we? Okay, so the x, that could be my a right here, and if we look on the on the right of that, the positive pi over 3 could be replaced, or could replace b. So let's state that before we get started. So we're going to say let big A equal x, of course, and everything's positive in this. So big B, capital B, is equal to pi over 3. All right. Now, we can now substitute these values into the identity, but we're going to do it in the context of this particular problem. So we're going to call this f of x, aren't we? So f of x is equal to 2 lots of, now it's the sine of x plus pi over 3. Now then, it's the second part of that product that we can replace. So all this is going to now be replaced by the right-hand side of this identity. Okay, it's going to be multiplied by 2, but that's okay. It's just a coefficient at the front. So everything in that purple box can now be replaced with what's on the right-hand side. So let's do that. So it's all together. So this is going to equal 2, and I'm going to open big square brackets here, and we'll put it in green inside. So it's going to be sine A cos B. So this is going to be sine x cosine pi over 3. Okay, using this part of the identity again, just to emphasize that, plus the cosine of A, which is cos x, multiplied by the sine of B, which is pi over 3. Okay, and you can close your brackets there. Now, this is quite useful. We've got 2 trig values we can actually evaluate quite simply. We've got the cosine of pi over 3, which is here. We can figure that out. And also the sine of pi over 3. Now, if you don't remember what they are, okay, of course you can use your calculator. Okay, so I'll just verify that with you so you're clear about what's going on. Okay, so we're on radians, so I can do the cosine of pi over 3 if you don't know it. So cosine of shift inverse pi, divide that by 3, close the bracket, and oh, it's a half. Isn't that wonderful? So we know that this value here is just a half. So hopefully this will trigger some memories now. So this is 1 over 2. Okay, and then if we do the sine of pi over 3, of course, if you're not familiar with it, you just go back to the calculator. So the sine of pi over 3, if you don't know, it's a standard one. Pi over 3, of course, is 60 degrees, and that's root 3 over 2. So we also know that this value here is root 3 over 2. So that's good. So I'll just get rid of the calculator now, and we can just complete the steps. So this is going to equal 2 multiplied by, and inside the bracket, I'm just going to put all that together. So it's going to be 1/2 sine of x plus root 3 over 2 cosine of x. And we're going to close the brackets here. And all of that is going to get multiplied by 2. So the final step, we're going to double everything inside there. So we're going to get sine of, that didn't go very well, sine of x plus root 3 cosine of x. And this is the harmonic form. Okay. There we have it. So you can see that it's the sum of a sine function and a cosine function, as well as being some kind of transformation of a sine or a cosine function. Although we've yet to prove the cosine version, but hopefully that makes some sort of sense. And I'll go back to the GeoGebra shortly, and then I'll show you that this is indeed the case. So what I would recommend you do now is, if you pause the video and see if you can repeat this task for case 2 using the cosine identity. And then hopefully you can see that you're going to get exactly the same function. Okay, so please pause the video, have a go at that, and then I'll show you the result. All right, so I've written out the full solution, and just to go through the steps here, notice that this time we've got A is going to be X again. And you can see in the identity, of course, that we're subtracting B, aren't we? So we subtract B there. So that means I can keep the B at pi over 6. It's a positive B because the subtraction is built into the identity. All right. And then all we have to do then is be able to figure out, once we've subbed everything in, we need to figure out what cosine of pi over 6 is and what sine of pi over 6 is. Okay, and you can do that on your calculator if you don't know. It's just the opposite of what we saw for the sine case. And then once you've expanded the bracket, multiplied everything by 2, you get exactly the same expression, albeit in the reverse order, but they are the same nonetheless. Okay, and if we go back to the GeoGebra file, you can see here we've got y equals sine x plus root 3 cos x in the corner. I'll just highlight that for you just to make sure you're really clear about it. That's what we've just derived this using the compound angle formulae, and we know from the overlay that they are of course all the same. So if I remove that, we've got sine of x plus pi over 3 multiplied by 2, which is the same as the cosine version, which is the same as the harmonic version. Okay, so I hope that's conclusive. I hope you're convinced by that. So let's go to the next stage and see if we can reverse the process. All right, so let's move on. Let's see if we can undo the process. So we've got case 1 and case 2 that we've looked at. And we know that the function can be represented in this general form, a sine x. So I'll just highlight that. It's really important. A sine x plus b cos x. Okay, oops, let's get the highlighter going. Now notice there's plus or minus there. Well, you'll see why later on. Okay, you can you'll notice that there's 2 variations. But how can we derive a function of only, so that's in bold, only sine or cosine from this function of this form? So in other words, how can we reverse the process? Right, well, there's 2 cases for this. We're going to look at case 1. So this is the sine version, and then we'll move on to the cosine version shortly. Right, so I'm going to need a bit more space. So I'll just scroll down. So case 1, we know that A and B are both positive. That's given to us in this example, and we're given the form that we want. Now it would be quite handy to see how does this form, particularly this part, how does it lend itself to the harmonic version? So how are these 2 things related? Well, we can find out by breaking apart the sine of x plus alpha inside the bracket. We can break this apart here using an identity, and then we can equate coefficients, and we can see hopefully how these 2 ideas are linked. Now let's do that. So I'm going to start off with the r sine of x plus alpha. So let's do this. So r is a positive value as well. And we're told that alpha is, of course, an acute angle. It's non-zero. So x plus alpha, this is the fish symbol. Okay, and we know we have an identity for all this. So let's use it. And it's an identity, so I can put the strengthened equals with the extra line. So we're going to keep the r where it is, and I'm going to open large square brackets, and I'm going to use the identity that we've met already, that you know a little bit now. And I won't write the whole identity out, but I'll just write out the right-hand side because that's the bit we're using. So it's going to be the sine of x multiplied by the cosine of alpha plus the cosine of x multiplied by the sine of alpha. If you're not convinced, please just cross-reference that with the previous page, and you can see that I've just used the identity from there. Okay, so we're just using the fact that the bit highlighted in yellow on the left is identical to the bit highlighted in yellow on the right. Right, what can we do with this? Well, we can multiply through by r, first of all. So we can do that. So it's going to be identical to r sine x cos alpha plus r cos x sine alpha. Right. Is there anything else we can do? Well, if we look at the harmonic form, so just go to the top of the page for a second, you can see, if you look at the sine x part, so it's a sine x, all right, here. Now, the sine x is maintained, okay, that stays as it is, and you can see the sine x is visible here as well. So it looks as though, because alpha is an angle, okay, that's it's not a variable really, it's just an angle, that a value that we need to find. Same way that r is a value that we need to find. We can treat the r and the cos alpha as a coefficient of the sine x. So in other words, the r and the cos alpha are just multiplying the sine x, okay? So what this means is I can write down an equation. So looking at the first part, we can see that r cos alpha must be equal to a. Okay? Simply because if these are supposed to match, then the r and the cos alpha must correspond to the a up there. So we have a relationship. So it's not it would be an equation if we were given the alpha and the r, but obviously we're not at the moment. So that's the first relationship. So I can write down that, and I'll call this equation 1. So that's the first thing we've deduced. And we can use the same reasoning. So we get to sort of go over this again in the second term of this expression. So if we look at the second term, we've got the cos alpha here present in both expressions, like that. So that means that the r and the sine alpha must be doing the same job as the b up here. Okay, it's a coefficient. So in other words, the r and the sine alpha must be the same as b. So I can write down yet another equation. So we now have that r sine alpha is equal to b, and we'll call this one equation 2. Right, so this is exciting. What are we trying to find? Well, we want to find out what alpha is, I think, perhaps. How do we do that? So we're assuming, of course, that in this situation, we know what a and b are, don't we? We're given that, and we have to express it in the r sine x plus alpha form. So how can we get alpha if we know what a and b actually are? Well, if you look back at your warm-up, you'll see a question where we dealt with this very thing. So is there some way of combining these two equations so that we can figure out what this alpha is? And the clue is in the fact that we have sine alpha and cos alpha. And if you haven't screamed it at the screen yet, I will put you out of your misery. So we can use the fact that tan alpha is, of course, identical to sine alpha over cos alpha. We can use yet another identity. We're going to use that idea. So what I'm going to do is I'm going to take equation 2 and divide it by equation 1. All right. Now, if I do that, I can bring the tan alpha into play. So let's set this up. So on the left-hand side, if I compare the left-hand sides of the equation, r sine alpha divided by r cos alpha must be equal to, and if we can compare the right-hand sides, b over a. Now, something else happens, which is quite good. The r, which is a non-zero amount, stipulated here, so there's no danger of this, that the r's are going to cancel out. So we're going to have cancellation with the r here and here. So they're going to cancel to 1, so that's good. So that means that we're left with sine alpha over cos alpha, which we know is tan alpha, which is just going to be b over a. So this is extraordinary. So if I'm given some harmonic expression like this, if I take, in this instance anyway, if I take the b and the a, which we know, divide them, that is the tan of the angle of the translation. All right, so that's really, really useful. So we're going to put this in a box and make it look really important. Really useful result there. So we found out what alpha is. Now, the other question is, how do we find out what r is? Because the r's have just cancelled. Well, we're going to be in luck as well, because the two equations contain sine and cosine. And if I'm clever, or if I'm clever enough, I can hopefully manipulate them in such a way to eliminate the cosine and the sine part. Now, you can do this a different way, but I think this is a more elegant way of showing you. So I'm going to show you this. I'm going to call it the proper way in inverted commas. So if we take equation 1 and square it, you can see, I'll just make a note of what I'm doing here. So I'm going to take equation 1. I'm just going to square that. Now, if you do that, just square the whole thing. So we'll get r squared multiplied by cos squared alpha would equal a squared. I hope that's okay. And if we do the same thing to equation 2, I'm going to square equation 2, and you can get ahead of me with this if you like. So we're going to have r squared multiplied by sine squared. Remember, you square everything in the expressions on both sides, would be equal to b squared. All right. Now, what can we do with this? Well, now I'm going to add equations 1 and 2 together. Okay. And when I say that, I mean equation 1 squared added to equation 2 squared. Note this is not good mathematical notation, by the way. It's just to help your understanding. So, yeah, don't write things like this in your exams. Okay, so equation 1 squared. Now on the left hand side, this is going to be the same as, and I'm just conscious of space here. Let's just try it. It's going to be r squared cos squared alpha plus r squared sine squared alpha. Okay, and if this is true, of course, this must equal the sum of the right hand side. So this must equal a squared plus b squared. Now, why is this good news? Well, if you remember question 1 from the warm-up, we have common factors of r squared in both of these. So we can factor it out. And don't worry, there's a couple more steps and we're done. So I'm going to factor out the r squared. So I'm going to have r squared. Now, inside the brackets, what we're going to have? Well, we're going to have cos squared alpha plus sine squared alpha. We'll close the bracket, is just going to be a squared plus b squared. Right, can you see what's going to happen? Well, all of that, for those of you who know your identities, inside out, back to front, and all the rest. That is just 1, irrespective of what alpha is, okay? It's an identity. It's always 1. So we now have a new relationship. We have the relationship that r squared is equal to a squared plus b squared. And if you prefer, if you want to, I'm just going to come over here just to finish this off because you've got a bit more space than I have. We can say that r, because it's positive, would be the positive root of a squared plus b squared. So it's a Pythagorean relationship, isn't it? So the coefficients a and b, if you apply Pythagoras' theorem to them to find a hypotenuse, you will get the value of r, which is the scale factor of the, it's the scale factor of the vertical stretch. I mean, it's absolutely remarkable how this all ties together. Okay, so we have 2 really, really important results there that look really good. All right, now again, if you could follow the process, I would suggest that you pause the video and try and replicate this, but using for case 2, so using the cosine identity. Okay, and see what results you get in this situation, and I will write up the solution momentarily. Okay, so let's have a look at this. So for the cosine version, very similar idea. We're going to have r cosine of x subtract alpha. And this is going to be identical to, so I'm going to, again, open the big square brackets, and I'm going to apply the cosine identity with the subtraction in it. So this is going to be, do this in green, this is going to be cos x cos alpha, okay, plus sine x sine alpha. So that's using the cosine identity, okay? And once again, if you're not familiar, they are in your formula book, so don't worry too much. So this part is absolutely identical to this part, irrespective of what x and alpha actually are. So let's continue. So let's multiply everything by r. So we're going to have r cos x cos alpha for the first term added to r sine x sine alpha. Be careful with your x's and alphas, don't get them mixed up. Now then, if we go back to the start of this, we've got this harmonic relationship up here, and we equate coefficients essentially. So let's have a look what we've got. So in the first term, we've got the r and the cos alpha. Okay, now that's the cos x part. Okay, so this is where we've got to be careful. The cos x, they will basically equal the coefficient multiplying the cos x. So in other words, they're going to be equal to b up here. All right, so it's in reverse order, but it's still doable. So just highlight that again. That's really important. The r and the cos alpha are multiplying the cos x. So they must be equal to b if we're equating coefficients. So that's our first equation that we can write down. So we have that r cos alpha is equal to b. And we'll call this one equation 1. Just check you agree with me on this. And then we apply the same reasoning to the second term. So we've got, in this instance, we've got r again, and we've got sine alpha multiplying sine x. So the r and the sine alpha must combine, and they must be equal to a. So that's our second equation. So we have r sine alpha equals a. All right, so we've got very similar looking equations. They're slightly different though, aren't they? Okay, and we can use the same identity. We can use the tan identity to work out what alpha is. So again, we will do equation 2 divided by equation 1. Let's do this. So we're going to have r sine alpha on the left-hand side of that equation. Divide that by the left-hand side of equation 1. So that's r cos alpha is equal to, now it's going to be a over b this time. All right, I hope that's okay. So the r's are going to cancel out, which is good. So that's going to be 1, that's going to be 1, and we are left with tan alpha. This is the final step, isn't it? So we get tan alpha is equal to a over b. So notice the subtle difference in this. Now, you don't have to memorize all these variations. What I would do is just be aware of how to use the compound angle formulae, which is what I've just done. And in 2 steps, you can get tan alpha, well, slightly more than 2 steps, 2 or 3 steps maybe. You can get the tan alpha is a over b without too much hassle. Okay, and it just saves you having to remember loads and loads of variations, and I think it cements your understanding a bit better as well if you go through this process. Okay, so you're just equating coefficients essentially. Now, once again, you'll notice that to get the r part, you can use the sine squared plus cos squared identity. Now, I won't go through all that again because it is exactly the same idea, okay? And you'll find very quickly you will get r squared. It's just going to be a squared plus b squared. I mean, because you're squaring and adding, it doesn't matter what the order is. So in other words, your r is just going to be the square root of a squared plus b squared. So for each of these variations, each of these cases, the r squared, or sorry, the finding r is exactly the same. Okay, it doesn't matter. You just apply Pythagoras' theorem to the coefficients a and b to get r. It doesn't matter what kind of question it is, you can always do that. So that's really important. The only thing you've got to be careful of in these is what the alpha is. Okay, there might be a slight variation on that. All right, so that's how we work backwards. So that's how we go from a harmonic trig function to some kind of transformation of sine or some kind of transformation of cosine.